welcome to the deep dive. Um, Today we are unpacking a really substantial stack of research and notes all about prompt engineering.
Yeah, it's a massive topic right now.
It is. But, we are not approaching this from the perspective of like a casual user trying to generate a recipe for dinner.
Right, or writing a polite email to your boss.
Exactly. We're looking at this strictly through the lens of a software developer.
Hmm.
Because, as you know, if you write code, there is a very specific comfort in the rigid, unforgiving universe of a traditional code editor.
Oh, absolutely. It's a controlled environment.
Right. You sit down, you open your IDE, and you write a function. And if you miss, like, a single semicolon, or if you pass a string where an integer is expected, the compiler just halts.
It completely shuts down.
It flashes red, it points a massive undeniable arrow at line 42, and it basically tells you that you messed up exactly right there.
And, I mean, it provides a beautiful deterministic boundary. You know the rules of the physics in that universe. If it compiles, it runs. If it throws a syntax error at 2 in the morning, which, is deeply frustrating, it is still incredibly safe.
It's predictable.
Exactly. The machine is doing exactly what you told it to do. Nothing more, nothing less.
But then you pivot over to an AI chat interface. You're staring at this blinking cursor in a blank text box, and suddenly all those laws of physics just evaporate.
They're completely gone.
Right. You type a loose conversational sentence, hit enter, and the machine just runs with it. There's no compiler to stop you if your logic is slightly fuzzy.
No, the system just attempts to guess what you meant.
And you find yourself in this sort of wild west of non-deterministic outputs.
Which is incredibly disorienting for anyone who has spent their entire career thinking in strict syntax.
No, I bet.
It feels less like engineering and more like trying to steer a massive ship by shouting vague suggestions at the wind.
That is a great way to put it. You have no steering wheel.
You really don't. But, the core thesis of our material today completely reframes this experience.
Okay, let's unpack this.
Prompt engineering is not just typing a good question. It is programming in natural language.
Programming in natural language.
Yes. You are writing executable logic for a neural network.
Okay, so that means we need a complete paradigm shift in how we view the text box itself. We have to stop seeing it as a search bar or a chat window.
Right. It's not Google.
It is a new kind of compiler one that parses English instead of Python or C++ run.
Think about the mechanical implications of that. For years, developers have optimized for strict syntax, but now conversational language is the syntax.
Wow, yeah.
And what's fascinating here is that the variability in the AI's output does not come from the machine's underlying capability fluctuating.
Wait, really?
Yeah, the underlying model is completely static during your interaction. You are hitting the exact same neural network weights, the exact same architecture, the exact same training data.
But the answers can be so wildly different.
Exactly. One prompt yields a genius-level architectural breakdown, while another yields a generic, totally useless summary.
So it's not that the model suddenly got dumber or, decided to be lazy on a Tuesday.
No, not at all.
The interface, meaning your natural language code, was simply sloppy.
Precisely. In traditional software development, if you write a terrible sorting algorithm, you don't blame the CPU for executing it slowly.
Right, you blame your algorithm.
Exactly. But with large language models, because the interface is so conversational, we have this dangerous tendency to anthropomorphize the machine.
We treat it like a person.
We do. If it gives us a bad answer, we say, oh, the AI is hallucinating, or the AI doesn't understand.
Guilty. I do that all the time.
Most people do. But in reality, the AI executed the ambiguous natural language program you provided perfectly. The prompt was simply poorly engineered.
Man, that is a crucial mindset shift for your daily workflow. If you write code, you really need to start treating your English with the exact same mechanical respect you give to your Python scripts. But that leads to an obvious problem. Conversational English is inherently chaotic. Right. It's ambiguous. It lacks the structure of an object-oriented language.
It's very messy.
So if natural language is the new code, how do we structure it so it doesn't just produce chaos?
Well, we need a framework, and the research breaks this down into a highly structured, 4-part anatomy of an effective prompt.
Okay, 4 parts. Let's hear them.
Every robust prompt, regardless of how conversational it might appear on the surface, relies on these 4 distinct components. First, the instruction.
The instruction, okay.
This is the explicit action you want the model to take.
Right.
Second, the context.
Meaning the background info.
Right, the background information required to ground the action. Third, the input, the specific raw data the model needs to process.
Oh, God.
And fourth, the output format, the exact structural requirements for the response.
While reviewing that breakdown in the notes, the developer in my brain just immediately lit up.
Oh, yeah.
Because what you were describing is basically just a traditional function call. Think about it.
I see where you're going with this.
The instruction is your function definition. It is the, def process data part where you declare the core action.
Right.
The context is your global state or your environment variables. The surrounding world the function needs to be aware of to operate correctly.
Yes, exactly.
The input is your parameters or arguments, the actual payload you are passing in to be transformed. And the output format is your return type. Are you returning a Boolean, a heavily nested JSON object, or a markdown table?
If we connect this to the bigger picture, applying that function call mental model is exactly how you turn a chaotic chat interface into a reliable, predictable engineering tool.
It makes it so much more tangible.
Let's look at a practical example. Say a developer drops a massive block of server logs into a chat window and types, "Find the errors in these logs."
Which people do every day.
All the time. But that is not a function call. That is a vague wish.
That is the equivalent of writing a function called dostuff and passing it a raw binary file without any parsing logic whatsoever. You have absolutely no idea what it's going to spit back out.
Precisely. Now, apply the four-part framework to construct it like an engineer.
Okay, let's build it.
Instruction. Analyze the provided server logs and identify any memory leak patterns.
Very specific.
Context. You are acting as a senior backend engineer, troubleshooting a Node.js application that crashes every 12 hours under high load.
Wow, okay.
Input. Here is the raw log data and output format. Return the findings as a JSON array containing the timestamp, the error code, and a one-sentence hypothesis of the root cause. Do not include any conversational filler.
When laid out like that, it completely sheds the feeling of chatting.
It's not a chat anymore.
No, you are defining the bounds of an execution environment and strictly typing the return value so it could be passed to the next step in a pipeline.
That level of rigor is what separates someone casually generating a recipe from a developer building resilient production-ready systems on top of large language models.
Okay, but let me push back on this a little bit. Because even if I write the perfect four-part function call, things still go wrong.
They do.
As a developer, I am deeply reliant on stack traces. If my Node application crashes, the system generates a block of text that tells me exactly where my code broke.
Right, it gives you a map.
I can trace it back to line 73 in a specific middleware file. If an LLM gives me a JSON array that is entirely hallucinated garbage, how do I know it's my prompt and not simply the model malfunctioning?
That is the million-dollar question.
Right. Where is the stack trace in natural language programming?
That is arguably the most defining struggle of the current AI era for engineers. The paradigm shift here is realizing that prompting is fundamentally an act of debugging.
Prompting is debugging.
Yes. You have to adopt a radical debugging mindset. When the model's output is wrong, the default assumption must be that the bug is in your prompt.
Which is incredibly unintuitive.
It is.
When the machine is generating the text, it naturally feels like the machine made the error. If it hallucinates a library that doesn't exist, my brain immediately says, the AI lied to me.
It feels like a lie, but under the hood, the model is simply a probabilistic engine.
Okay.
It predicts the next most likely token based entirely on the context window you provided.
Right, the tokens.
So if the output is a hallucination, it means your prompt created a context window where those hallucinated tokens were statistically the most probable path forward.
Wow.
So to answer your question about where the stack trace is, your output is your stack trace.
Wait, so the bad output itself is the error log.
Exactly.
I need to read the hallucination to understand where my English was ambiguous?
Yes.
Yeah.
You iterate by diagnosing the delta between what you asked for and what you received.
Okay, that makes sense.
If the model gave you a summary that included information outside of your provided input data, you look at your prompt. Did you explicitly write, use only the provided input data and absolutely no prior knowledge?
Right.
If not, the bug is right there. The model drifted because you didn't fence it in. You left the probability distribution too wide.
We really have to stop blaming the black box and start treating the prompt as mutable code that needs refining.
We do.
If the JSON is malformed, my reaction shouldn't be to just hit regenerate and hope for a better dice roll.
Never just hit regenerate.
I need to tighten the constraints. Add to the output format instruction. Ensure the JSON is strictly valid with no trailing commas and wrapped in a raw text block.
You iterate, adjust the parameters of your natural language, and test again. This is why test-driven development concepts translate so beautifully to prompt engineering.
Oh, that's a brilliant connection.
You write your prompt, you run it against a suite of 10 different edge case inputs, and you observe where the output fails your assertions. Then you debug the English.
Which brings up a really fascinating trap that I see all the time. And I mean, I am guilty of this myself.
Oh, what's the trap?
Because debugging an LLM requires tweaking the prompt, engineers often try to over-engineer their solutions.
Oh, yes.
We love complex architecture. If a model fails at a basic task, an engineer's first instinct is to build a massive multi-agent lane chain loop, or implement a semantic routing layer, or like string together a dozen API calls just to force the model to behave.
It's true. We instinctively reach for architectural complexity when we should really just be focusing on syntax.
It is like trying to implement a distributed caching layer using Redis across 3 continents before you have even bothered to optimize your basic SQL query.
That is a perfect analogy.
You are adding massive infrastructure overhead to solve a latency problem that a simple inner joint could fix.
Exactly.
So in the prompt engineering world, what is the equivalent of writing that optimized SQL query?
The research is unequivocal on this point. Clear, specific, and explicit instructions are, quote, unreasonably effective.
Unreasonably effective. I love that.
It's true. Before you reach for advanced tooling, before you orchestrate agents or fine-tune open-source models, you must exhaust the potential of good, simple instructions.
That phrase, unreasonably effective, suggests we severely underestimate just how much computational heavy lifting plain, explicit English can do if we take the time to author it well.
We really do underestimate it. This raises an essential question for anyone building with AI. How often do we assume the model lacks the reasoning capability for a complex task when our initial instructions were simply ambiguous?
Oh man, probably all the time.
Right. A developer might write, make this function better, and then get frustrated when the model changes the formatting instead of optimizing the time complexity.
Because better doesn't mean anything.
Exactly. Better is a highly subjective, inherently ambiguous word. A traditional compiler would throw a fatal error if you typed make better.
It absolutely would.
So your prompt engineering standards shouldn't accept it either.
It all comes down to clarity over cleverness.
Always.
A seasoned engineer knows that writing clever, unreadable code is a sin because it makes debugging an absolute nightmare. The same applies to prompting. Yeah. A convoluted, massive paragraph of rambling instructions is going to confuse the model's attention mechanism. It literally loses focus.
It dilutes the signal.
You want crisp declarative sentences. Refactor this function to reduce time complexity from O of n squared to O of n log n. Do not alter the existing variable names. That is explicit.
And mastering that explicit clarity is what unlocks the more advanced capabilities of these models.
Okay, so where do we go from there?
Well, if we are disciplined with our instructions, what happens when we remove the training wheels entirely? Can the model deduce the logic without us mapping out every single step?
Oh, this brings us to the frontier of prompting, doesn't it?
Yes.
Yeah.
Specifically, zero-shot prompting.
The holy grail of AI interactions.
Yeah.
The idea of getting the model to perform a highly complex reasoning tasks with absolutely no examples provided. Just the raw prompt and the input data.
In the early days of large language models, few-shot prompting was mandatory.
You had to give examples.
You had to. You had to provide 3 or 4 examples of the exact input-output pairs you wanted, just to force the model to recognize the pattern.
Right.
But modern instruction-tuned models have fundamentally altered the landscape.
Let's translate that jargon for a second for everyone listening. Instruction-tuned models are models that have been specifically fine-tuned by researchers to understand and follow human commands.
Yes.
They aren't just blindly predicting the next word to finish a sentence anymore. They have been mathematically trained to recognize that when a user gives an imperative command, they should execute it.
And because of that instruction tuning, they are remarkably adept at zero-shot tasks.
It's wild to see it in action.
It is. If you provide that rigorous 4-part function call structure we discussed earlier, these models can synthesize novel solutions without needing handheld examples.
But the way you frame the task in a zero-shot scenario becomes a critical lever, right?
Absolutely.
I'm endlessly fascinated by the task framing aspect, especially what we call role prompting.
Oh, role prompting is powerful.
I use this daily, and it always feels like a psychological trick, even though I know it is just math.
It does feel like magic sometimes.
It's the practice of framing a task by telling the model to adopt a specific persona. For instance, you say, act as a senior database architect with 20 years of experience in high availability systems.
It feels like a parlor trick, but it is purely statistical routing.
Explain that. How does the math work there?
To understand why this works, we really need to demystify what a latent space is.
Okay.
Imagine a massive, multi-dimensional database where all human knowledge is mapped out as coordinates.
Like a giant galaxy of concepts.
Yes. Topics related to security vulnerabilities are clustered together in one distinct zip code, while topics related to basic syntax errors are clustered in another.
Okay, I follow.
When you use role prompting, you are essentially pre-filtering the probabilistic pathways the neural network is allowed to take.
So by invoking senior database architect, I am giving the model the exact coordinates to that specific zip code in the database. I am bringing all the specialized vocabulary, the stringent constraints, and the typical problem-solving frameworks associated with that persona right to the forefront of the model's attention weights.
Exactly. Let's look at a concrete code review example.
Okay.
If you simply ask the model to review this code, you are pulling from a very generic center-of-the-map latent space.
You'll get generic advice.
Right. It might point out a missing semicolon or a poorly named variable. But if you frame the zero-shot prompt with a role, say, act as a strict security-focused code reviewer looking for OWASP top 10 vulnerabilities, you radically shift the model's attention weights.
It bypasses the generic syntax checks entirely.
Yes, and it statistically pulls concepts like buffer overflows, SQL injection, and cross-site scripting to the top of its probability distribution.
So I have literally changed the environment variables of my natural language program.
That's a great way to think about it.
And the fact that we can achieve this level of specialized analysis with just a dozen words of English, rather than writing 1,000 lines of configuration code, I mean, it demonstrates the sheer leverage of prompt engineering.
You are loading a specific context module into the runtime before executing the instruction.
Wow.
It changes everything about how the neural network retrieves and processes the information you give it.
So, what does this all mean for your daily workflow? We have covered a massive paradigm shift today.
We really have.
We started by moving from the rigid, comforting safety of traditional syntax into the fluid, non-deterministic world of natural language programming.
And we explored how to tame that chaos.
Right, by structuring our prompts like 4-part function calls.
Yeah.
Instruction, context, input, and output format.
We also discussed embracing the debugging mindset.
Yeah, recognizing that when the output goes off a rails, the output itself is our stack trace.
Exactly. We have to assume the bug is in our prompt and iterate with the precision of a test-driven developer.
And we highlighted why simple, clear, explicit instructions are unreasonably effective.
Which means we should optimize our natural language before reaching for complex architectural workarounds.
Exactly. And finally, we looked at how zero-shot prompting and role assignment can dynamically rewrite how a neural network processes our code by shifting its attention weights to highly specialized clusters of knowledge.
It's incredible leverage.
It really is. This isn't just some quirky new tool to generate boilerplate code. This is a fundamental expansion of what it means to write software.
It demands a new kind of rigor.
It does.
The syntax may have changed from semicolons and curly braces to verbs and adjectives, but the core engineering discipline, the need for clarity, strict structure, and systematic debugging, that remains exactly the same.
It really makes you wonder about the future of the profession.
It does.
We started this deep dive talking about that blinking cursor in the IDE and the comfort of the strict compiler that only speaks code.
Right.
But as that compiler evolves to speak fluent, nuanced English, it leaves us with something to ponder.
What's that?
If programming is evolving from mastering rigid mathematical logic to mastering clear, explicit natural language, what does that mean for the future definition of a software engineer?
That's a big question.
Will the most valuable technical skill of tomorrow simply be the ability to communicate perfectly today?
A fascinating question to leave you with. Until next time.